Hello everyone, I'm Radhika Achikanath Chirakkara. I'm a first year PhD student working at the Australian National University. I would like to thank the organizers for this opportunity to present our study in this specialist discussion meeting on galactic magnetic fields. Today I'm going to talk about the efficiency of the small-scale dynamo in the highly subsonic regime and its applications to primordial magnetic fields. I'll start with the motivation for our study, which is the lower bounds on the intergalactic magnetic field strengths inferred from gamma ray observations. The plot on the right is taken from one of the first studies which explored the lower bounds on the intergalactic magnetic field strengths from Fermi observations. We see here that the lower bounds on the field strengths improve with the correlation length of the magnetic field when it is much smaller than scales of megaparsecs. Many studies have looked into the origin of these fields present in the voids of the universe and have attributed them to either astrophysical or cosmological origin. The observed IGMF value in many cases are orders of magnitude greater than the magnetic fields generated in the early universe. In our study, we are interested in the cosmological origin of the IGMF. Seeds of magnetic fields are expected to be present in the early universe, and Wagstaff et al. 2014 proposed that a turbulent small-scale dynamo acting in the early universe can amplify these seed fields to explain the lower bounds on the present-day IGMF value inferred from gamma-ray observations. The turbulent small-scale dynamo is a mechanism that efficiently amplifies magnetic fields by converting turbulent kinetic energy on small scales into magnetic energy. The magnetic energy growth by the small-scale dynamo depends on nature of turbulence, the longitudinal or rotational nature of velocity fluctuations, the compressibility of the plasma, the kinetic Reynolds number, the magnetic Reynolds number, and the magnetic Prandtl number. The small-scale dynamo has been studied in different astrophysical settings, for example, the formation of first stars and first galaxies. Now coming back to the early universe dynamo, Wagstaff et al. Find that turbulence can be injected in the primordial plasma due to primordial density perturbations or first-order phase transitions that may occur in the early universe. The velocity fluctuations injected by these mechanisms are primarily longitudinal or compressive in nature. The small-scale turbulent dynamo is also expected to have operated under very subsonic conditions in the early universe with a Mach number of around 10 to the minus 4. In our study, we try to understand the properties of the small-scale dynamo in this previously unexplored highly subsonic regime for different turbulent driving models, and we primarily are interested in the purely compressive driving of the turbulent dynamo. We simulate the small-scale dynamo using the Flash code, and we solve the 3D MHD equations on a uniform computational grid. The MHD equations are closed with an isothermal equation of state. The turbulent driving field F, which injects energy into the plasma in this momentum equation, is modeled using the Ornstein-Uhlenberg process, and we drive turbulence on half the size of our simulation box and define the eddy turnover time as the driving scale divided by the velocity. This is a schematic of the stretch twist fold dynamo model, which amplifies magnetic energy exponentially. The solenoidal fraction zeta in our turbulent driving models controls the vorticity being injected in our simulations. Zeta equal to 0 means we are not injecting any vorticity in our simulations through the driving. So this is called the purely compressive driving case. Zeta equals 1 is the purely solenoidal driving case. We study the purely compressive and mixed driving models where zeta is a number between 0 and 1. Vorticity in the plasma plays a critical role in the small-scale dynamo action, and its evolution is governed by this equation here. Since we have an isothermal equation of state, The pyroclinic term cannot generate any vorticity in our simulations. When zeta is 0, or in the case of purely compressive driving, in the presence of density gradients through viscous interactions, the final term on the RHS of the vorticity equation can generate some vorticity, which can be amplified by the nonlinear first term on the RHS of the vorticity equation. When zeta is non-zero, we continuously inject vorticity into the plasma. And in this case, we see that the solenoidal fraction of the kinetic energy increases. We study the amplification rate gamma, the saturation efficiency, and the solenoidal fraction of the kinetic energy as a function of zeta and the Mach number. Here we have some of our turbulent dynamo simulations as a function of time. The top panel shows the Mach number, the middle panel shows the magnetic energy, and the bottom panel shows the magnetic energy divided by the kinetic energy. From the middle and the bottom panels, we clearly see exponential amplification and saturation of magnetic energy by the small-scale dynamo. We also see that at the same Mach number, faster dynamo action and higher saturation efficiency happens when you have a higher value of zeta in the simulations. Here we have the saturation efficiency of the dynamo and the solenoidal fraction in the kinetic energy as a function of the Mach number for all the turbulent driving modules that we have studied. We also performed some non-ideal MHD simulations and find that our ideal MHD simulations have a kinetic Reynolds number of approximately 1500 and a Prandtl number of 2. We find that the solenoidal fraction of the kinetic energy is intimately linked with the growth rate of the small-scale dynamo and its saturation efficiency. And we find that when zeta is 0, or when we do not inject any vorticity in our simulations through the driving, vorticity is still generated in the plasma and can lead to small-scale dynamo action. We find that for all the models that we have studied, turbulent dynamo is efficient in the low Mach number regime. We apply results from our purely compressive driving model to the results from Wagstaff et al. 2014. And we find that when driven by primordial density fluctuations, the early universe turbulent dynamo can generate magnetic fields with strengths greater than 10 to the power 16 Gauss on scales of 0.1 parsec. If the small-scale dynamo is driven by first-order phase transitions, which may occur in the early universe, the dynamo can generate much higher field strengths greater than 10 to the 13 Gauss on scales of 100 parsecs. Field strengths generated by the early universe dynamo are compatible with the present-day IGMF inferred from gamma ray observations on scales of 0.1 parsec and 100 parsecs. We also note that these values are lower limits as the magnetic field generated increases with the saturation efficiency of the dynamo, which is likely to be higher in the case of the early universe. To summarize our findings, we studied the properties of the turbulent dynamo for a broad range of Mach numbers between 10 to the minus 3 to 0.4 for 5 different forcing models. In the highly subsonic regime, the solenoidal fraction of the kinetic energy increases for both the purely compressive and mixed driving models. In the highly subsonic regime, the saturation efficiency of the dynamo increases for all the turbulent driving models we have studied, and the growth rate of the dynamo also follows a similar behavior. The field strengths that we obtained from our dynamo models with results from Wagstaff et al. 2014 are compatible with the present-day value of IGMF inferred from gamma ray observations on scales of 0.1 parsec and 100 parsec.